Johnny Chan and is entitled Structure and Track Changes Associated with Tropical Cyclone Landfall.
Thank you, Robert. Well, I don't know if I should talk about this anymore because Robert said that all the models are wrong, so whatever I'm going to say will probably be wrong. This actually is a shortened talk from the one that I gave in the landfall processes workshop last October in Shanghai. So if any of you were there, you could probably go and have a cup of coffee or sleep for the next 15 minutes. Anyway, so for those of you who were not there, that will be something that you might want to listen to. So the talk is on the changes in track and structure associated with tropical cyclone landfall. So we'll be talking about track and also the convection distribution, these two issues. So the changes in the track, this is more of a summary of some of the previous studies that I've made. Very simple modeling study. This is an F-plane experiment in which you have land to the west of the domain and sea in the eastern part of the domain. And this is the nested grid, and we'll put a storm about 150 kilometers prior to landfall, next to the east of the land. So if it's an F-plane, then we should expect no movement. And in fact, this is a case where you don't, if you have the domain very homogeneous in terms of moisture and in terms of friction. So S means smooth and W means wet. So you have lots of moisture and very smooth domain, and the storm doesn't move, basically. If you put land to the western side, in the sense that you are making this dry and making this wet, but the friction, the roughness length is exactly the same between the green and the blue. The storm still doesn't move. However, if you make the land to be much rougher than this, make this part of the domain much rougher than that over the eastern part, and W means wet, so the moisture is exactly the same between these two areas. You see that the vortex is actually drifting towards the southwest with some sort of a looping motion, but basically drifting towards the southwest. The last one is when you have rough land and dry land, so you will see that these two cases are very similar. So the conclusion from these four experiments is that when you have a rough surface, a discontinuity in the roughness length, then you expect a vortex which is supposed not to be moving, tend to be attracted towards land. So that's an interesting result, I think, assuming that the microphysics is correct. So let's focus on this result and analyze it a little bit more. So if you look at the asymmetric flow in this experiment after 1 day, this is in the boundary layer, so it's from about 900 millibars to the surface. And this is called it's the asymmetric flow, so you subtract the symmetric part of the circulation. And what you expect is that because the flow is cyclonic, so if you subtract the cyclonic part, then as the flow goes over this rough land over here to the west, then you would expect the wind to slow down, so the asymmetric flow gives you a convergence over here. And similarly, on the offshore side, you will have divergence. So that's what you would expect, and the wind speed is not very large. So that's nothing exciting. What's interesting is that if you look at the lower layer, which is from about sigma from 0.9 to 0.55, what you see here is that it's actually exactly opposite to what you see in here. So in other words, on the onshore side, you have a divergence, and in the offshore side, you have convergence. So in other words, you actually have this low level. So on the onshore side, you have low level boundary layer convergence, and then you have mid-level divergence. So you have this secondary circulation going on, and similarly over on the lower level. But the speed is not very large. It's only less than a meter per second. in the upper level, the flow is very weak, so we won't go too much into that. Then after 6 days, when the vortex is drifted right over land, same thing if you look at the boundary layer, very similar. You still have convergence here, divergence here, and this arrow indicates the direction of the motion, so the storm is drifted from here to there in about 6 days. And now if you look at the lower layer, then that's what you see. You see actually it generated a pair of gyres, where you have anticyclonic flow here and cyclonic flow here, very much like the beta gyres that you have in the beta plane, but this is an F plane. So this is another set of gyres that are generated because of the frictional differences. Now, what you see here is that the flow is not, it's appreciable. It's about 1 meter per second, and but the flow direction is not exactly the same as the movement of the vortex, and I'll explain why in a minute. Now, in the upper level, very similar situation where you have a pair of gyres, although not as well defined as this one here, but you still see this anticyclonic flow and cyclonic flow here in the upper levels. So the difference is because of the PV budget. Chun-Jae asked this question, and also I guess Robert mentioned that, is that if you look at the PV budget during the asymmetric, this is the wave number 1 decomposition, and the horizontal advection term, which is this upper right hand corner here, as if you recall, that this pair of gyres has a if you like a ventilation flow that's going almost from north to south, and so therefore if you look at the horizontal advection of potential vorticity, you would expect to have a positive tendency here and a negative tendency here. But the direction of the motion is like that, and the reason for this is because it's offset to a large extent by the diabatic heating term, which is on the lower right hand corner here. But if you add these two together, you basically get a maximum PV tendency along the line of where the storm is going. The vertical advection tend to be quite small. So in other words, the reason why there is a drift of the vortex towards the southwest is because of a combination of this horizontal advection as a result of the generation of the gyres, and then the diabatic heating as a result of the asymmetric convection, which I didn't have time to go into. Now, so that's very simple. What if you put in the beta effect? So this is same experiments, but then now you put in the beta effect, and so of course the beta effect will cause all the vortices to drift towards the northwest. But I'm showing you the 3 experiments here. This experiment is rough wetland, so the same thing here is this is rough but it's wet, and this is rough dry, and this is smooth dry. So let's just try to focus on the same experiment, which is rough dry. Now if you focus on this experiment, the black line is the control experiment, and the red line is when you have rough land here and rough and dry land over here. So if you focus on here, you see that there is a little bit of a drift, and it's about 15 kilometers. And now this model has the finest resolution is 5 kilometers. So this is probably not a problem with the resolution itself. So it's probably real. But more interestingly, if you have a land surface that's instead of north-south, it's an east-west oriented coastline. So if you focus on the same thing here, rough and dry land, so you see that there's also a deviation. Control again is